do this rather quickly. And then I want to explain sort of physically what is an instanton and what is a sphalerons and how are they different and how do they answer different questions. And then discuss applications to both QCD and the standard model. So I want to talk about instantons and sphalerons in QCD and the standard model. And the topics are to discuss topology in QCD and the standard model. And the previous speakers have actually done a lot of my work for me here. So I will in how we try to compute these things. But what I'm actually going to do is the first two things in the reverse order. I'm going to start by explaining what is this notion of instanton and sphalerons and how are they different and how are they answering different things. Mithat, you have a question already?
I think Mithat still has his hand raised from earlier, and I believe Antonio, you still have your microphone open, so probably you want to.
I'm sorry.
Yeah, actually, Soeren, you can put down people's hands.
Yes, I am sorry. I wanted to lower it, and I will.
Okay, everything's good. Okay, so I'm actually going to start and spend quite a bit of time explaining, so what is the notion of instanton and sphalerons, and when do I want one and when do I want the other? And there's a beautiful toy model for understanding this, which was presented by Arnold and McLaren in 1988 in a very nice paper called The Sphaleron Strikes Back. But nevertheless, I find that even now there are a lot of people who are a little bit confused about this. And so I thought I would go through this nice toy example, which makes it particularly clear what is an instanton, what is a sphalerons, when do I want one and when do I want the other. So consider a pendulum where I have a fixed length bar and a mass at the end of the bar. So here's my Lagrangian, and I'm going to consider it quantum mechanically. It's in a gravitational field, and so it has a potential, 1 minus cosine theta potential. And this Lagrangian is actually not enough information to specify this problem as a quantum mechanical problem. Because when this angle phi goes through 360 degrees and the pendulum swings fully around back to its starting position, these two situations, 0 degrees and 360 degrees, are physically equivalent. And so I have to choose a boundary condition for how to treat the wave function when it wraps from 0 to 360 degrees. And so there's a phase e to the I theta associated with the periodicity of the wave function in terms of this periodic variable. So when you come 2 pi around, does the wave function match or does it differ by a phase? And we're used to thinking about these phases, theta equals 0 being bosons and theta equals pi being fermions. And in some settings that's correct. And in this setting, this phase can be anything you want. And one question would be, how much does the physics depend on this phase? And basically the question, how much does the ground state energy or the free energy at finite temperature depend on theta? That's going to be answered by instantons. And to what extent does this pendulum physically actually spin around? How often do I go over the top and experience this 2 pi periodicity in real time? That's the thing determined by sphalerons. So let's go through that. So let's think about the pendulum in vacuum. Why does that theta matter at all? Well, consider the potential as a function of the angle phi, and then think about what the wave function should look like. And the wave function should have a peak at 0 where the potential energy is the smallest. And then at larger angles, it should be falling away where the potential energy makes it expensive. And the question is, so it gets small here, but does it go to 0? And if theta is 0, then it needs to match whatever happens over here and whatever happens over here, they need to match here, which means that there's a, it's positive here and it's positive there. But if theta is pi, then it has to match antiperiodically. If it comes down positive here, then that means that the image is negative. And that means that the function has to have a 0 here. And putting in that node in the function means that the energy will be higher. And the fact that the function is very small here means that this energy splitting will be small, but it's there. There will be a higher energy. And you could estimate how much higher that energy is by finding out just how small is the wave function here using, say, a WKB approximation. And that's essentially what we're going to do. That's what the instanton is going to give us. So the energy, if theta equals 0, is lower, and if theta equals pi, the energy is maximal. Okay. Someone else's microphone is on.
Guy, I had a question. So here you mean you're solving the Schrodinger equation in this periodic potential. That's what your
Yes.
psi is, right?
Yes, I'm
Okay,
I'm solving the Schrodinger equation in a periodic potential with a twist on the boundary condition. Yes.
Yeah, thanks. Yeah.
Yeah. Okay, so the easiest way of finding the energy dependence of this theta is to do exactly that. You solve the Schrodinger equation in this potential with this boundary condition. It's easiest, but maybe not necessarily the most insightful. We learn something also by considering and using the path integral formalism. Because the path integral formalism sort of picks out in a nice way when is the how often does essentially it finds this amplitude of how big the wave function is here in a different way by thinking about how often does a path jump through pi. And so a computation using the path integral, one set of paths which occur, in fact, the only paths which can occur that care about theta is a path that starts at 0 and ends at 2 pi, or starts somewhere and ends somewhere plus 2 pi. If a path has to end either at the same as the starting value or the same value modulo 2 pi. And when that 2 pi modulo is there, then the path gets weighted by an e to the I theta. And when it's not there, it doesn't get weighted. So the only way theta ever arises is from paths which switch by a multiple of 2 pi. And an easy way to estimate the effect on the vacuum energy is to find the vacuum to vacuum transition element with e to the minus beta h that returns the vacuum energy. And I can make a reasonable approximation for this thing by asking about the phi equals 0 to phi equals 0 or 2 pi transitions. And then the part that picks out the theta dependence is the transition in this path integral from starting at theta equals 0 to ending at theta equals 2 pi. And there's a semi-classical solution which does exactly that, which is what I've drawn here. It starts near 0, and at some epoch, it switches from one to the other. And we'll call that an instanton because it occurs in one specific epoch or instant in time. And that's how Electroweak came up with this name. And actually, this isn't a precise moment of time. There's a width here, which is characterized by the natural scale in the problem, which is the inverse frequency. So the vacuum energy gets a contribution from all non-trivial numbers of 2 pi jumps. And those are weighted by a phase, and they're determined by these amplitudes. So the first one of these looks like that, where this SI is the action of this instanton jump. And this contribution, I know, is going to be proportional to beta, because this didn't have to happen at this moment. It could have happened at this moment or at this moment. In other words, the curve I drew is one possibility, but it could have happened here, or it could have happened here, or it could have happened here. And there's a single parameter where that happened, which I know I'm going to have to integrate over. And my answer is going to be linear in that parameter. And so I know that this quantity is linear in beta, and I'm going to name the thing after I divide out that linearity SI prime, and that thing is independent of beta. And that's the thing that's actually going to give me a shift in the vacuum energy. So the vacuum energy will turn out to go as cosine theta, and this will be exponential in this zero mode reduced action for the instanton. So there's an exponentially suppressed shift to the vacuum energy, and it's exponentially suppressed because the wave function here is exponentially small. So that's sort of expected. And the size is given by the zero mode amputated instanton action. Okay. This calculation actually, when I write this as an exponential, the first term is the thing we had here. The second term, when I expand this exponential in this thing, is an expression where I have two of these transitions. It can go over, and then it can go over again to 4 pi, or back to 0. And assuming that these events are rare, but that this time is large, then I can have two well-isolated occurrences of this switching over. And I actually need to resum those if the log of this extent is of order the size of this suppression. And then I'm in a regime where multi-instantons are relevant, but if this exponential suppression is large, then they're well approximated as the sort of a product of individual instantons. Okay. So what happens at finite temperature? Well, actually, I was already calculating at finite temperature because this beta here is actually the inverse temperature. And here I was considering, since I said I was doing the vacuum and I was finding this energy, thinking of it as the vacuum energy, I was making beta very, very large. And if I don't make beta large, then I'm actually calculating the free energy as a function of t, where t is 1 over beta. And so I just consider this to be, honest to goodness, a finite extent. And I say, so how do things change as I make that extent, say, larger or smaller? And if this extent is large enough that my instanton comfortably fits inside of it, then not much changes. But if I go to higher temperatures where this extent is smaller than the width my instanton wants to be, then my instanton has to switch from looking like this to being sort of cramped. And as I make my temperature higher and higher, the instanton has to run across faster and faster. And because of this contribution to the instanton's energy, that means action, sorry, that means that the action of the instanton actually grows linearly in the temperature. And that means that the exponential suppression of these processes gets worse and worse. And in this case, it's linear in the exponent, which is giving you the exponential suppression. So as you go up in temperature, the effect of this theta angle very, very rapidly disappears. We saw in Maria Paola Lombardo's talk that for QCD, it won't vanish quite so rapidly. Rather than a linear dependence on temperature here, you only have a logarithmic dependence. But for this model, it's linear. And what does that physically mean? Well, it means that the instanton has less and less influence on the free energy. And if the question you want to answer is, how does this theta angle influence the free energy? The answer is that it has less and less influence. And the reason is because in vacuum, the free energy is determined by the ground state. At finite temperature, there are contributions from excited states. And the ground state, you recall, wanted to be symmetric at this point. The first excited state actually wants to be antisymmetric at this point. The first excited state looks like this. Its wave function psi of phi has a node at 0. And so it's positive over here and it's negative over there. If I continue periodically, that means I'm negative over here, and these things have to cross at another node. But if theta is pi, so that the wave function is supposed to continue anti-periodically over here, then this negative is positive over here, and I don't have a node here. I have a minimum, but away from 0, and we know that that is going to give me a lower energy. And so as I increase theta, while the vacuum energy rises, the first excited state energy falls. The second excited energy rises, the third falls, and it's actually, it flips depending on the parity of the wave function. And now when I only care about this guy, then you see that the energy is going to go up. But when I average in some way over many states, then there's a lot of cancellation between those where it's going up and those where it's going down. And the result is that the free energy actually has a weaker and weaker dependence on this theta. And this is what we explicitly see in this. In this case, the calculation is easier to see what's happening in this instanton picture than it would be by trying to solve many, many excited state wave functions. So trying to find exactly what all of these energy shifts are is very hard. But we can sum the effects of all of those shifts at once in this instanton picture and see that the exponential suppression of how important this theta is getting stronger and stronger. Okay. So that's the answer to the question, how much does the free energy depend on a twist angle? Let's ask a different question. Does the value of phi change? What if I watch this pendulum and I see what happens? In vacuum, the pendulum just sits here. Maybe it bounces back and forth a little bit, but it's almost never going to shoot over the top. In fact, it can only do so by very rare tunneling processes. But as I crank up the temperature, then sometimes it should just fly over the top. There's a suppressed but finite chance, Boltzmann's suppressed chance, that it has enough energy to just be sitting here on the top. And you know that if it is, and if it has just a little bit more energy so that it's moving, that the time history that thing is going to follow, just semi-classically, is that it's going to just spin around. And so you actually expect that as the temperature gets higher, the extent to which this field physically changes value of this angle in real time will get faster and faster. So whereas the effect of this theta angle becomes smaller and smaller, the real-time transitions in this angle become more and more common. So for some processes, that's physically important. So let's try to understand that better. Okay, so because in order to better represent what happens in all of the physical cases which we'll be interested in, I'm going to couple this pendulum to a thermal bath. The reason I'm doing that is that if I don't, if this thing has the energy to go over the top, then it will just fly around and around and around forever. If I couple it to a thermal bath, then sometimes it'll get lucky and have the energy, and then down here we'll lose the energy, it'll sit around at the bottom for a while, and then it'll get kicked by the thermal bath and go over again. And that makes the problem sort of more entertaining, that there are individual isolated transitions instead of some things in your ensemble just going around and around and around and other things in your ensemble just sitting. But I'm not going to be very specific about my coupling to the thermal bath. The only issue is how strong is the damping. And we'll see how much that actually influences my my physics, but I'm assuming that when I wrote my Lagrangian, that was actually the Lagrangian with somehow renormalized couplings, taking into account the effects of this thermal bath. Okay. So sometimes the pendulum gains some energy, enough to go over the top, and then it'll spin, it'll lose some energy, it'll bounce around at the bottom again, and then it'll gain some energy and be able to go around the top again. So we'll have occasional 2π transitions. And if I wait long enough, those transitions will be independent of each other. It might jump, it might fly around the circle clockwise one time, and then a while later, it will instead fly around counterclockwise. So one time it gets kicked a bunch of energy, it will fly this way, and then it'll get stuck at the bottom. And then there's an even chance that the next time we'll go over that way or we'll go over that way. And the result is that it's going to make a random walk on long time scales, sort of the staggering drunk type random walk, and you know that that means that the squared angle is going to increase linearly in time. And so I'm just going to call the linear growth rate over very, very long time scales where we're adding up multiple 2 pi jumps, the Sphaleron rate. So the definition of the Sphaleron rate is over very long time scales, how much do these 2 pi jumps accumulate? Okay, and there are 3 parts, semi-classically, there are 3 parts to that. The first part is how much of the time are you at the top? The second part is when you're at the top, how fast are you moving? And the third part is how correlated are different crossings to the top. This third part is determined by this damping I talked about. So to see that, let's again draw this potential as a function of phi, and I'll draw in a couple of minima like that. And now imagine that I have my pendulum and it's rocking around in here, and it gets a kick from its thermal bath and has enough energy to jump over the top. If the coupling to the thermal bath is very weak, then in the time it takes the pendulum to go down and come up here, it still has enough energy to go over. And so it's going to make a couple of transitions in a row and then finally get a kick which makes it settle into the next minimum, and it'll lie in here for a long time until it gets kicked hard enough that it'll go somewhere else. These 3 crossings then are correlated with each other. They're all automatically in the same direction. And that's going to give me a larger transition rate. On the other hand, if I go to the other extreme, where I have a very large damping rate, then what's going to happen is that the thing will manage to get to the top, and then it will immediately get kicked and turn around and go back over the top, and then maybe get kicked and go again. And so actually there can be several crossings here, and those several crossings all add up to a total of either 1 crossing, if it's like that, or no crossings, if it's like that. And in this case, the total rate of crossings is smaller than the microscopic rate of times that it crosses exactly this line of pi. So here the crossings are anti-correlated with each other. The damping is very strong. But there's a nice big wide range of dampings when everything is fine, because here's the energy 2 mgl, and here's the energy 2 mgl plus T. And typically when it goes over the top, it has this much energy. And if that's enough energy to bring it from here to here, then it'll make it over the top without bouncing back and forth. Sorry, if the damping is such that it can make it this far without losing T, then it'll make it over the top in 1 shot. But if the damping is enough that going this whole distance is enough to lose T, then it'll get stuck here. So there's a wide range of damping strengths where the damping is weak enough to let it go over the top, but strong enough to catch it in the next valley. And in more complicated situations where instead of just the location on the top of a hill, we're talking about some complex nonlinear thing, then generically this is going to be the case, because it's going to roll down and it's not going to be aimed precisely to go up the next hill. It's going to be aimed to shoot off in some other direction. So the generic thing is that you're in this regime where then the individual crossings are uncorrelated with each other. And we can get on with our life. In that case, the only question is, how often is it crossing this magic phi equals pi or 2n plus 1 pi barrier? And how often it crosses that barrier is the product of how often it's at the top and how fast it's moving. So to see that, imagine defining a little region here. And what I can ask is, what's the total probability to be in this region times how fast it moves through that region. If I make that region narrower, then there's a smaller probability to be in that region, but a shorter time that it takes to move through. And so the probability to be in the region divided by the time to cross region, actually, technically, it's times the mean inverse time to cross the region. This is the thing which gives me the transition rate. So this will give me the Sphaleron rate up to this issue of subsequent crossings being correlated, which I'm for the moment going to ignore, but one could in principle go back and figure that out. And so the relevant physical question is, it's two questions now. How often are you at the top? And how fast are you moving across the top? How often you're at the top is the same as in the path integral. How often do you have a path which is sitting at pi? Specifically, if I make a narrow range around pi, how often do I have a path which starts and ends inside that range? The question, how fast do you move across the top, turns out to be up to a easily computed numerical coefficient. The question, how big are the fluctuations back and forth around pi when you happen to be there? If I give something with a very, very large inertia, then it's going to typically move very slowly over the top here. And the large inertia is also, when I calculate paths here, it's going to suppress paths with big fluctuations and you'll be paths with very small fluctuations. But if I give a very small mass, so I have a very small inertia, then it's going to typically fly with a large momentum. And that's also going to give me paths which have big fluctuations here. And we'll use that later. Oh, and why on earth do we call this a Sphaleron? So I explained Instanton. So what's the word Sphaleron all about? Well, this funny guy, Nick Manton, who came up with this, thought this is something that's sitting at the top of a hill, or in a higher dimensional situation, you would say that it's, so this is a 1 degree of freedom problem. Real problems that we'll be interested in have many degrees of freedom, but they still have some kind of a valley here and a valley here and a maximum, and then many, many other directions which go up. And the point we're interested in is sort of a saddle point. Just Anyaban, you have a question?
Yeah, thank you. Just wanted to, I couldn't. So you said that when it's crossing, so the temperature gives this extra amount of energy which helps it to pass through on top of it, not.
Yeah,
and
so
then
the temperature does two things. It gives us enough energy to get up here.
Right.
But generically, you don't have exactly that amount. You have T extra, right?
Mm-hmm.
The most common thing to happen is to have 1 T extra more than you need. Okay, so
yeah, and
a typical thing which flies over the top by an amount where its extra energy is about T. And that determines how fast it flies across. Flying across way up here is more suppressed, just because there's Boltzmann suppression of being up there. Turns out flying across here, you're going so slowly that it also doesn't happen very often. So sort of the sweet spot is to be about 1 T above.
Okay, so in this combination, the d phi dt is going to be affected by that temperature.
Right, so I have an energy which goes as m d phi dt squared. So then you can see that the sort of typical value of d phi dt is going to be, there's some units missing here. Yeah, there's probably an L squared here, yeah. The typical value is going to be T over ML squared, okay? And so you see that T enters in determining how big this is, and M enters in the denominator, that if I give you a large mass, then this is small and it goes over slowly. And this same large mass also suppresses, oops, oh, I erased it. That's why I can't find it. It suppresses transition, it suppresses the path integral wiggles at the same time. So the size of the path integral wiggles are related to this thing. And so you actually see this quantity also in Euclidean space, which is non-trivial. And we'll need that. Okay, so if I talk about something more complicated, in a field theory, there are many, many degrees of freedom. One of the degrees of freedom plays the role of this phi. We'll see which one in a minute. And many other degrees of freedom are then stable directions, and this is a saddle. And so the sphalerons is something which sits right in the saddle. The saddle is slippery, and so they looked up the Greek word for slippery, and it's sphaleros, and so they named this thing Soeren. And now we're stuck with it. Okay, so that's sphalerons and instantons. And if there's any question about sphalerons and instantons where you need me to be clearer or more explicit about something, this is a good time. Otherwise, I'm going to continue to applications. Okay, so let me talk about topology and gauge theory. And this I'm going to do super fast because the previous speakers today have actually covered most of what I wanted to say already. So we start out by thinking about n-component scalar theory. And for simplicity, I'll think about n equals 2 and in 2 dimensions. I am then going to have a spontaneously symmetry breaking wine bottle potential. And to better visualize what's happening, you can, as a function of x and y, you can plot what phi 1 and phi 2 are doing, so that at any point you can describe the field with a vector. And then if the number of components here happens to be the same as the number of space-time dimensions, then a description of the field looks just like a vector field. And if you think about vector fields, well, I mean, it can vary in some kind of random way like this, or it can also vary in a more interesting way where if I cut out some point and I say, I don't know how to define my vector. Oh, sorry, I should mention something. This wants my field to have a fixed length f. So it's not just any vector field, it's a vector field where at every point the vector has the same length. And then if I try to define that everywhere in the xy plane, except at one point, then one interesting solution is phi 1 equals x over r and phi 2 equals y over r, which looks like this. This is not the electric field of a charge because the length is the same at every point. Okay, and this is a smooth field doing a smooth and sensible thing except at this point. And it's impossible to define this field in a smooth way at this point. And it's impossible to change around the field a little bit. There's no way I can change the field in this region, for instance, and get rid of the fact that there's some screwed up point. It's impossible. And the way to see that it's impossible is to consider what happens as I go around the edge of this region to the direction that the field is pointing. Here, the field is pointing this way. Here, the field's pointing this way. Here, the field's pointing this way. Here, it's pointing that way, that way. As I go around this loop, the direction loops around. And by continuity, I can draw any smaller loop, and it has to loop around as I go around this loop. And that is true by continuity unless there is a discontinuity. And so I can shrink the loop down to 0, and the only way that I reach a contradiction if I can shrink the loop down to 0, because this always changes by 360 degrees, and you can't change, a continuous field can't change by 360 degrees around a point of 0 size. So either at some point as I'm shrinking this loop, I cross a singularity, or I'm shrinking this loop onto a singularity, but there has to be a singularity somewhere in the middle. And nothing I can do to adjust the field inside of this region can prevent there from being at least one singularity. So there's topological information out here that tells you that there must be a singularity here in the middle. And this isn't the only topological solution. Any solution which has this winding property is also topological. So for instance, another nice solution looks like this. And this sort of makes it clearer that what's happening is that the field is corkscrewing as you go around this point, but this is actually just a rotation of the first thing I wrote. So I put a y here and a minus x here. And you see that I've just performed a 90-degree rotation on this field and gotten another solution, which will have exactly the same property. And there's also solutions where it corkscrews the opposite direction. So I can change by 2 pi, or I could also change by minus 2 pi, or any multiple of 2 pi, but it's quantized. Okay, and the same thing can happen in 3 components in 3 dimensions on the surface of a sphere around some sad point now in x, y, and z. I can have phi 1, phi 2, and phi 3 point always on the normal of this sphere. And the same thing will happen. That will be somehow wrapping non-trivially around what's happening at that point, and there will be no way to contract it where I don't have the direction wrap over a sphere. And the same thing happens with 3 spheres in 4 dimensions and so on. This is relevant to QCD and to QED, where it's easier to see. So, sorry, the standard model, the SU2 of the standard model, where it's easier to see. So let's think about SU2, which is a toy model for SU3 of QCD, but it's also directly the weak interactions in the standard model. And it turns out that the group SU2 is isomorphic to S3, which is the same as the set of possible vacuum values for this field if I were in 4 dimensions. And so the same kind of winding that we saw here and that we saw here can occur in 4 dimensions with something which behaves like S3 or like SU2. To see that SU2 has this property, note that the most general possible element of SU2 is the exponential of some Pauli matrices times some angles. And if you carry out that exponentiation, it gives you a cosine of the angle times the identity, and then a sine of the angle times the Pauli dot the direction of the angle. And this is 1, 2, 3, 4 elements. And so if I call this coefficient phi 4 and these 3 coefficients phi 1, phi 2, and phi 3, then the sum of the squares of these 4 fields have a total length of 1, because cosine squared plus sine squared is 1. And so I can think of the amount of cosine and the amount of each Pauli as 4 directions, and the group SU2 as being the 3 sphere in that 4-dimensional space. So there's an isometry between SU2 and the 3 sphere, which is defined in this way. Okay, and therefore, if I choose SU2 values through space, except at some point, then I can have the SU2 values wind as they go around that point in exactly the same way that we talked about with scalar fields here. And now that's relevant because, so let's think about gauge fields on the 4 torus. I'm taking the 4 torus as a toy model of space-time. But you could argue it's actually not even a toy model of space-time. It is space-time. So it's the space-time that lattice people like to use because it has very convenient properties. Namely, locally, this space is flat and you don't know that you're in some compact thing. You could think that you're in an infinite universe. And well, because of exactly that, we actually don't know. Maybe the universe we're in is actually 3 torus. And the 4th direction is just that we're not in vacuum, we're at some temperature, and I can make the extent of the 4th direction beta, the inverse temperature, just be really big to represent the fact that we're at some very low temperature, much lower than any temperature relative in QCD. And this length is bigger than the current horizon of observations in cosmology. And then I really have no idea whether maybe actually the universe is a box, and it's just such a big box that we can't see far enough to see around the box. So this is a perfectly valid description of the universe we live in, or could be, okay? And gauge fields, so the true gauge field, let's say the gauge field is a connection of a SUN bundle on this space. But we can describe that connection using coordinates, which we call the gauge potential, A mu. Except, as you know, when you try to describe some non-trivial object using coordinates, sometimes you can't do that globally. So for instance, on the Earth, you cannot choose a set of coordinates to describe the surface of the Earth, which are everywhere free of singularities. Typically, we choose to cut out the North and South poles, and then we have a perfectly good set of coordinates which can describe, so here's the Earth, and we choose these latitude and longitude coordinates, and they work fine, except at this point and at this point where the coordinate system becomes singular. So similarly, when I want to describe A mu, that's actually a coordinate system on the connection. And it might be singular somewhere. But if I cut out a point or a small region around one point, then I can actually guarantee that the geometry is then trivial enough that just like cutting out the North and South poles, I can now guarantee that I can define this gauge potential everywhere in the remaining space away from this point. And unless I'm stupid and pick a point where the field strength diverges, then if I make this little cutout very, very small, I can neglect the field strength at that point, which means that my gauge field will be pure gauge and can be described as some kind of a covariant derivative of a gauge transformation matrix defined over this little sphere. And this gauge transformation matrix is an element of SUN, which for SU2, we've already seen is equivalent to the 3-sphere. And so this is a 3-sphere I'm wrapping over a 3-sphere, and it can be topologically non-trivial. So one thing that could happen for SU2 is that the pure gauge, A is lambda inverse TA del mu lambda trace, is going to be determined by this lambda. And what this lambda could be is it could, at the North Pole in space around the singularity, it could be in the North Pole in the in SU2, and on the East Pole, it could be the East Pole of SU2, and on the West Pole, it could be the West Pole of SU2, and on the South Pole, it could be the South Pole of SU2. And on the, I don't know what you call this, the Greenwich Pole, it could be the Greenwich Pole.
Kai, you have about 10 minutes left or so, just so you know.
Oh boy, okay. So what's interesting is that if I ask about a chunk of this space, then I'm going in some direction here, some direction here, and some direction here to pick out a 3-dimensional piece of volume. And those correspond to going in some 3 directions in my gauge space, which picks out a volume of my gauge space as well. And the way to count that gauge space is to integrate over my surface the wedge product of my A's in 3 directions. This epsilon picks my A's in 3 orthogonal directions, and this F picks the 3 directions in this lambda space. And so this combination tells for each piece of physical space how much of the gauge field space have I covered. And if I've wound over this physical space in my gauge space, then the area I cover here will be equal to the area of the 3-sphere, which is 16 pi squared. It's 2 pi squared because that's the area of the 3-sphere, except that there's an extra 2 somewhere from here, from Pauli matrices and stuff. And so there's an extra times 8, and then there's an extra 6 because this 6-fold overcounts. Okay. And so this is the thing which integrated over this surface gives me something which is topological. And then if I add something which is harmless because it involves a field strength, which I assumed was small, then I end up getting something whose total derivative equals the famous FF dual. And so if I integrate in the rest of the box what FF dual is doing, then that, because FF dual is a total derivative, that integrates to what K is doing over the surface, which is this topological quantity. And so this quantity turns out to always to be an integer. And that's the instanton number. And if I do that integral over only part of the box up to some surface, then that's the thing I'll call the Chern-Simons number. Okay, and then there's this trick that it turns out that FF dual is always smaller than the action. And so the best you can possibly do is to have the action equal to the integral of FF dual. And that's how we get this bound that having an instanton always costs 8 pi squared over g squared, which means that these topological configurations at recoupling will be exponentially suppressed. And now we want to look for these things in path integrals. And we already saw that there's 2 different kinds of things I might want to look for, instantons and sphalerons. The instanton is when you have a full transition in your periodic time range. And that means you have a blob where the integral of FF dual over that blob is this topological amount, 32 pi squared. Okay, and as you move from underneath to on top of this blob, the Chern-Simons number on the surface rises from 0 up to a quarter, up to a half right in the middle, to 3/4 to 1. And it's this change by an integer amount from 0 to 1 that tells you that you've gone through topology. The Sphaleron, so this blob is equivalent to what we did back here when we swung from 0 to 2 pi. We had nothing, and then in some region we swung, and then we reached 2 pi, and that's the same here as having, where am I? Nothing, and then having a blob, and then being at Chern-Simons equal to 1. And the instanton, the Sphaleron, is the thing where you take a slice of precisely the middle of this thing, which is something which doesn't know whether it wants to be closer to this vacuum or to this vacuum. And you just duplicate that across the time direction. And that's the same as sitting exactly on the top of this saddle. So you should think of the instanton as being like a path. Here, why don't I do this in another color? So here's Chern-Simons number, which is playing the role that phi played before. It can go from 0 up to 1. And there's some energy which peaks in the middle. And the instanton is a path where you go from being here over the top to being here. And the Sphaleron is the state where you sit at the top. So the Sphaleron is 1 dimension smaller. And so what I do is I make the middle slice of this thing be 1 point in Euclidean time, and then I just have it duplicate and be exactly the same all the way across. So the Chern-Simons number is a half all the way across. And that's the Sphaleron. This is the thing that controls whether you go through this thing from one topology to another. And this is the thing that determines how the free energy cares about whether there's topology. So let's see, applications. So what about instantons? When do I care about instantons? And the answer is, well, in QCD, I care about instantons because besides the standard action of QCD with fermions and with bosons, nothing stops me from sticking in FF dual with a parameter theta, which plays exactly the same role as the theta we saw in the toy model. It gives an extra phase when one of these transitions happens. And if this phase is 0, then you have the lowest vacuum energy. And so the free energy cares about the value of this theta, and the topological susceptibility, which we saw in Maria Paola Lombardo's talk, is essentially how much does the free energy care about the value of this theta. And it's approximately the coefficient on a 1 minus cosine theta term in the free energy as a function of this theta. And so for that, we want to know to what extent do these instantons actually happen. But that doesn't tell you all the information. It tells you the information about how strongly the ground state energy depends on this theta, which is super interesting if there's such a thing as an axion particle. So that could be a topic for another talk. But there's another application where sphalerons are really important. And to understand that, you need to think about what the fermions are doing in all of these backgrounds. And here I'm going to concentrate on SU2 of the standard model, which is the interesting property. How long do I have now, Soeren?
Yeah, not so much longer. Maybe like 5 minutes or so.
Okay, yeah, I'll manage somehow. Okay, so SU2 with the standard model only couples the left-handed quarks. The left-handed quarks also couple to a Higgs. And because of the Higgs, they have a massive dispersion. If you look at the energy as a function of momentum, then there's a branch up here of positive energies, there's a negative energy branch, and according to the Dirac interpretation, these are all filled states and these are all empty states in vacuum. And then if I fill one of these states, that's a particle. And if I empty one of these states, that's an antiparticle. And so promoting one of these guys up to here, leaving an empty thing and a filled thing here is a particle-antiparticle creation. But if I have a Sphaleron process, so if as a function of time, physical, real Minkowski time, if at some moment I'm right in this Sphaleron, the middle slice of an instanton, then surely the fields are going to wander their way towards one vacuum on one side and towards the other vacuum in the past, so that it's a transition as a function of real time, which looks a lot like a long, elongated, stretched out instanton, going from Chern-Simons 0 up to 1. When Chern-Simons is 0, as I'm in vacuum, then I'm in vacuum. But as I move up here, exactly at the Sphaleron, there's one fermionic state with 0 energy. Where did that come from? Well, at the beginning, that was one of these negative energy states. And then as I moved up, it slid from this sort of valence band up into this gap to 0, up above 0, and into this sort of conduction band. And since these are all filled, it shows up here as a filled state, which means that if this process occurs, I get a filled state here, but I do not have any empty states down here. That's particle production. At the end of this process, I have a quark, which I didn't have at the beginning, and no antiquark. And this happens separately in each color, in each generation. So this delta NCS equals 1 creates a baryon number of 3. That's 1 in each generation. And it also creates a lepton number of 3. So baryon and lepton number are violated. If I go up to a high enough temperature that these sphalerons happen, then I'm going to see baryon and lepton number violation. And that's exciting. It might explain the matter-antimatter asymmetry in the universe. So there's really interesting applications in the standard model of sphalerons. And there could also be applications in QCD if in heavy ion collisions, one somehow produces a left-right imbalance, then that imbalance this same process happens in the left guys, but in the right-handed guys, a particle at the top finds its way down to the bottom, and so you would have a delta Q left of 3 and a delta Q right of -3. Well, I mean, this isn't 3 anymore because it's NF. So in the QCD version, you have NF transitions in left-handed and minus the same number in right-handed, and so you create a chiral imbalance of fermions, or you relax a chiral imbalance. So if somehow you got a chiral imbalance, then the same processes would be a relaxation process for it. So it's also physically important in QCD. How fast do these sphalerons occur? Well, this was actually calculated in the 1990s in the Electroweak model, because you can make justified semi-classical approximations. And the classical field system can be calculated in real time. In QCD, that probably doesn't work. At any interesting temperature, the coupling is too big for the same techniques to be considered reliable. But if there's just a minute left at the very end, I'm going to tell you about the new way we have for calculating this. How do I compute instantons in QCD? Well, you go to Maria Paola Lombardo's talk and you listen to it again, because the whole talk was about this issue. But here and basically what she said, to review, is that at low temperatures, you can do it accurately with chiral perturbation theory. And at very high temperatures, you can do it with perturbation theory, this dilute instanton gas. So you calculate how common are instantons. And in between, the instantons aren't very reliable. Chiral perturbation theory fails. And you have to use a lattice treatment, which towards the upper end becomes very challenging and requires some kind of reweighting techniques. But that's a matter for another talk. So what about the Sphaleron rate in QCD? Well, I'll give you a super fast 1-minute version. Think about the toy model that we saw. What we're interested in is the product. So here's the Euclidean time direction. It's periodic from 0 up to beta, which is 1/t. And here's the Chern-Simons number. It goes from 0 up to 1. And there's a special value of ½ And what we want to know is how often are you very close to a ½ So what's the probability of being in here? Because that's the thing that tells you how often you're at the top moving across. And then the other thing we want to know is dn dt, because that's the thing that tells you how fast you transition through a Sphaleron. And this is determined by how big the fluctuations are when you're at the top. And so if you're not quite at the top, then you have a path which looks like that never quite reaches this 1/2 line. But if you're close enough to the top, then you have a transition. Here, why don't I erase these guys? Come on, erase, man. Then you have something which will just, slip over this line here and there. So actually what you want is how often, how many paths cross the n equals 1/2 line. Or in particular, if I pick two surfaces separated by beta over 2, how many paths are on opposite sides at these two surfaces? So how many times does a path start off on this side of the line, and over here it's on that side, and then it crosses back to this side? And up to a constant of proportionality, which is easily calculated, this gives you exactly the product of these two things, which is the thing you need to determine the Sphaleron rate. And so if I can figure out, is a configuration on this side here and on this side here, then I can use that to determine the Sphaleron rate. And I can do that by asking, when I apply gradient flow, does it flow down to here or does it flow up to there? And as we'll show in a few months when we finish the paper, this gives a complete prescription for describing the Sphaleron rate in QCD. Okay, so that's all I wanted to say. So in summary, instantons are tunneling transitions between vacuum sectors, and they're relevant for questions like the vacuum energy. Sphalerons are real-time transitions, and they're relevant for some real-time dynamics, and they're very, very different from each other. And our toy model gave us a very clean physical picture of how different they are, and why this one tells us about free energies and why it gets smaller and smaller as you go to high temperature. And this one tells us about real-time dynamics, and it gets bigger and bigger as you go to high temperature. Non-abelian gauge theories have topology. I gave a super fast introduction, but I think we heard a lot more about that in previous talks today. And sphalerons are physically important in the electroweak theory. They could explain the abundance of matter in the universe, and they may be important in QCD for things like chiral imbalances. Instantons are needed in QCD if there is a hypothetical axion particle. I didn't have enough time to describe that in great detail, but you can ask me about it offline. And some of these calculations are well controlled. The sphalerons in the standard model, instantons in QCD are coming under control. And we think now we have a new technique to discuss sphalerons within QCD. Okay, thank you.
All right. Yeah. Thank you very much, Guy, for this great talk, really.